So back to small fields, I'm sure most of you are aware of the Technical Report Series 483, the joint publication from the AAPM and the IAEA. But they do define small fields in that report as having at least one of three conditions. So either loss of lateral charge-particle equilibrium on the beam axis, partial occlusion of your primary photon source by the collimating devices, or the size of the detector is similar to or large compared to your beam dimensions. So scanning in these fields, of course, is a little bit extra tricky compared to normal size fields. So the first thing I like to look at when choosing detectors is how the detectors themselves impact your small field measurements. So for scanning specifically, your volume averaging is really the key point on the detector size and the detector shape. Your field profile compared to your detector spot size, the area over which that field is integrated, as well as in any imbalance between the axes of your detector, depending on which direction you're scanning. With a spherical type chamber, you would have equivalent volume averaging, whether you're scanning in line with the chamber or across the the direction perpendicular to the chamber axis, whereas you get different volume averaging with an elongated chamber, which a lot of scanning chambers are. Accuracy in your positioning, both within your tank, it's a little easier than setting up, say, a phantom in order to scan and find the center of the field, but consistent and accurate positioning is, of course, quite critical with small fields as well. Choice of detectors impacts your measurement as well through perturbation of the beam. Depending what you're putting into the beam, you're replacing water with some material, whatever it is in your detector. And so you're actually perturbing the fluence of the beam. You're changing the radiation interactions right there at the point of measurement. And so several things to consider as you're choosing these detectors. If you're looking at an ion chamber, how big is your air cavity, especially compared to these small field sizes? For a diode, what is the density of the diode? Is there any built-in compensation? Sometimes there's an air gap or some lower density material next to the diode in order to attempt to balance the interactions and bring it back more into a water equivalent sort of realm. That can impact your energy response as well. Diodes usually have at least some energy response. They tend to over respond to some of the low energy scatter. And for scintillation detectors, it's just making sure really, is this scintillator water equivalent material for my beam? And if not, then there may be corrections that need to be applied for those. Third consideration is the signal you get from your detector. With an ion chamber in particular, the signal is directly proportional to the conducting volume. So the smaller you push your ion chamber, the less signal you get. And for a well-calibrated electrometer, like our Supermax or our Max 4000 electrometer, the low signals can be handled very easily. With a water tank scanning electrometer, some of those don't have quite as low a range as some of the calibratable electrometers, or the ones that you would use for your TG51 measurements. And so you do have to be a little bit extra careful about making sure that your electrometer is not operating in a range where you're mostly getting electronic noise, or you're not getting very good stable signals. So your signal to noise ratio does become more of a concern as you get down into these low signals. Again, because of the capabilities of the electrometer that you might be using it with. For a diode, you get a much larger signal than you get from micro-ionization chambers, but of course there are trade-offs for that as well. And with a scintillator, this is also a small signal device, and small signal levels usually mean you have to scan slower in order to get less noisy measurements. Signal to noise ratio comes into play in terms of the leakage of your electrometer, a proper electrometer warm up, or I should have put the bullet point in here, just the low end of the range of measurements for your electrometer. It's good, if you can, to match signal strength of your detector to your proper electrometer range. I know, again, a lot of the water tank scanning electrometers don't necessarily have a range selection. They have a single range that they operate in. But if you're using, for instance, our Doseview 1D water tank with either the Supermax or the Max 4000 electrometer, then it's very easy to make sure that you, or you have a low range, you can select it for use with those depth scans for the 1D tank in particular. Accuracy of your measurements is another thing to be concerned about. Not, of course, we're concerned about accuracy of the measurements. To consider how accurate do I need these measurements to be? And in terms of that accuracy, you have to consider things like energy dependence. If you have a 0.5% variation in response due to energy dependence, but you're comfortable with a 1% uncertainty in your measurement, then that may not be something you need to consider as carefully as if you're really trying to get the highest accuracy measurements possible. In terms of the diodes, the energy dependence is affected by things like energy compensation that has been built into the diode. They can under-respond out of the field and give you kind of a large region of lower dose measured doses looking that are lower than what the actual doses are, which can result in underestimation of dose for the low dose regions in your SRS patients, for instance. Corrections due to energy dependence, for those who've read TRS 483, those can be both depth and field size dependent because of the change in the spectrum as you're blocking your source, as you get the occlusion that happens with the small fields. And then, of course, changes in scatter conditions. We're pushing the envelope here in terms of lateral scatter. You're likely to be operating in a lack of equilibrium condition in terms of the lateral scatter, and so that does affect the response of your detector. That's, again, why there are correction factors for these small field sizes in TRS 483. But it affects scanning as well, not just output or strict dose measurements. Angular dependence of your detector can come into play. Usually with water scanning, we're not as concerned about that, but I have heard of people trying to turn a diode on their side or something like that, and you do get some angular dependence. You do get different response in those orientations. You might have a different energy response as well due to the attenuation through the diode. So I usually advise you use your detectors in the orientations they were designed for, or at least be aware that there may be some implications of changing that orientation. Ion chambers in particular have dose per pulse dependencies. There are some dose rate dependencies that manifest in other detectors as well. So it's good that you understand both the way your accelerator increases the dose rate, if it really is just an increase in the rep rate of the pulses, or if there's an increase in the dose per pulse, and how that might impact your detector as you're scanning these fields. So with that said, kind of those concerns out of the way, which detector should we choose? Which one would I recommend? Well, we've got several options. The first, of course, is the ion chamber. The Exradin A26 is a very good quality micro chamber. We have the D1V for the scanning diode, and then, of course, the scintillation detectors, near and dear to my heart, the Exradin W2. So all of these detectors, and from anyone else as well, but all detectors have both strengths and limitations. And so oftentimes your best solution is a good combination of detectors. There are, for instance, the scintillator for very small fields, you have to scan a little more slowly, may not be the best for across the board crossing to large fields as well. But there are some good balances that can be achieved with a good collection of detectors. So in terms of the ionization chamber, why I recommend the A26, this one was designed in response to some investigations that revealed all microchambers that were on the market at that time had some very strange behavior in terms of polarity response and ion recombination. And so this was designed following the investigation that kind of pinpointed the cause of some of those strange behaviors. We made it so that the spot size is spherical, so it doesn't matter what your orientation is, your volume averaging will be consistent. We modeled the electric fields to verify the size and the shape of that active volume. The chamber volume compared to the normal scanning chamber of the A28, which is a 0.125 cc, you're about an order of magnitude lower. So your signal level is going to be correspondingly lower. It's not quite as small as our A16 chamber, but that one has a wire central electrode, so it does behave slightly differently. However, in doubling the volume, doubling the signal that you measure from this volume, you really only pay for it with a fraction of a millimeter in terms of the increase in the spot size of the chamber. Strengths of ionization chambers in the A26 in particular is a reference class ionization chamber, so you can expect a nice stable behavior from that one. The spot size, as I mentioned, is independent of the orientation. It is a spherical active volume in this tiny thimble. And ionization chambers really are familiar technology for most physicists, so it's a comfortable choice. We understand if we see some odd behavior, if we see leakage, we understand where that comes from. We understand how to do some troubleshooting on it. And you're able to operate within your comfort zone, I think, with this detector. Limitations really are size. It's a small ionization chamber, but it is an ionization chamber. There is a size element to it that's larger than some of the other detectors that we have. And you do get some small perturbation due to the fact that you have air in your beam at that point. The use of conducting plastics on this helps minimize some of those perturbations, but we can't get around the fact that there's air there. With our diode, we do have two orientations available. So the D1H, the horizontal orientation, was really for solid phantoms. For scanning, it's the D1V, this vertical orientation, in order to minimize water motion as you're scanning through the field. It's really the same diode in a different housing. So if you see publications for D1H versus D1V, it's the same physical diode, just a different case. It's an unshielded diode with a 1 millimeter diameter spot size, so it's a nice fine resolution on your images there, or your scanning point. There are correction factors if you're doing output factor type measurements. There are correction factors that have been published on that one, but in terms of scanning, it's a nice stable one for scanning with a good high signal. So strengths of the diode is that it is a well-established technology. Diodes have been around for quite some time and have been used regularly for relative field scanning. There's minimal volume averaging because it's the nice small 1 millimeter diameter active area, and there's a low angular dependence. There is a little bit. I wouldn't turn it on its side for your scanning. Then we have a different orientation for that if you want, but it does have a little bit of angular dependence if you were to get way off axis. Limitations, as with any diode, it's not water equivalent. It is a little more dense, and so you do have some energy dependence. You can see here the publication from Paulo Fasascan, where there is a little bit of energy dependence compared to something like the water equivalent scintillator. The scintillator then, my favorite, sorry. You have to put up with me. I like the scintillator. It is an organic scintillator material. The W2 has a user replaceable fiber, so we have options for you to have either 1 by 1 millimeter active area or 1 by 3 millimeter active area. The reason to have both, honestly, is twofold. One, the 1 by 3 millimeter matches the W1, the first generation device that we released. Goodness, how many years ago now? That there were a lot of publications on the W1, and to be able to do that direct comparison then with the exact same fiber, just with the W2 setup, is nice for some people to have that tie back to those original publications. The other reason is that you get 3 times the signal from the 1 by 3 millimeter active region compared to the 1 by 1. So if your field can handle that additional volume averaging, it does make your scanning a little bit less noisy, a little bit faster if you use the larger scintillator compared to the very small one. However, there's the option for that ultra fine resolution if you need that 1 millimeter resolution for the really small fields. Our scintillator is water equivalent for all of the MV photons and electrons, so you don't have to worry about that energy dependence. You do, however, have to correct for Cherenkov light. So this is that characteristic blue glow from a reactor coolant pool. We create that blue light in this PMMA optical transfer fiber when it gets irradiated. You also have to give it a reference dose. You have to give it a known dose if you want to have output in terms of dose. That, again, doesn't really matter for your scanning as you're doing a relative measurement. But you do have to recalibrate both. The CLR stands for Cherenkov light ratio, recharacterize that, do a recalibration for dose if you want to have output in terms of dose as the material accumulates dose. So the reason that you have to repeat this is because these are clear plastics. They do yellow as they get irradiated, and so as they age, the spectrum that gets transmitted through the fiber changes slightly, and therefore the magnitude of the signal that we measure, since we're measuring that optical light, it can change. One of the biggest advantages of the scintillator is the fact that it is water equivalent. This is backed up by that publication from the IAEA. They list correction factors for different energies. This happens to be the 10 FFF and, well, FF and FFF table. They list correction factors for all kinds of detectors as field sizes decrease. And the scintillator is the only one in this publication that has correction factor of unity for every single entry that it shows up in. So that is nice in terms of peace of mind, just knowing that you're not missing that energy correction as the field sizes decrease. We use a 2-channel chromatic correction to get rid of the Cherenkov light. This is based on a publication from Matthew Guyot et al. From back in 2011. This is really what enabled us to make a commercial device with the scintillator in the first place. And we've got a blue scintillator. That's this curve here. Cherenkov is a broad spectrum additional light, stem effects, contaminant light, whatever you want to call it there, but additional light that's generated depending on how much optical fiber is in the field. So we have you do a set of characterization measurements. We call them a minimum fiber and maximum fiber configuration. And really what it is in minimum fiber configuration, you have the fiber coming straight out of the field. On a maximum fiber configuration, you're wrapping the fiber around, so you have more of the optical fiber within the field, but you're keeping the dose to the scintillator itself the same. So if you have 2 measurements then with only the Cherenkov contribution changing, we can look at the change in signal of the blue channel compared to the change in signal in the green channel and use that to create a correction factor called the Cherenkov light ratio. So then subsequent measurements, we use the magnitude of the green signal multiplied by that ratio to remove the Cherenkov from the blue signal, and this has been shown to be quite stable. If you want to do a dose calibration, it's just a scaling factor that's multiplied by this in order to convert the units from collected charge to dose. So you would give it a known dose and a reference field size in order for the system to calculate that correction. With the W2, it's got its own dedicated electronics. This has both the optical signal processing and the electronic processing to remove the Cherenkov. You can do point dose measurements with this device itself, but for scanning, it does a very fast Cherenkov correction for every 10 millisecond integration, and then converts that corrected value into an analog output, a current that is read then by your water tank scanning system. So what that looks like is here. We have this W2 in the DOSE 3D water tank. There's an adapter sleeve that comes with it that really is just a stem adapter to increase the size of the fiber stem so that you can hold it in a standard scanning chamber holder pretty much in anybody's water tank. That optical signal then is read in by the, sorry, I'm getting a telephone call. Read in by the MaxSD, which is that dedicated electrometer. That Cherenkov correction is done rapidly. and then the current is sent to your water tank scanning electrometer. So from the standpoint of the water tank, it looks like a diode. You're not applying bias to the detector, but it's receiving a signal anytime that the beam is turned on. So strengths of the W2, its water equivalent for megavoltage photons and electrons, has that beam quality correction factor of unity. There isn't any dose rate or energy dependency. There is a negligible temperature dependence. It's about 0.1% per degree Celsius. So as long as everything you're doing is at room temperature, you're just fine. If you happen to fill your tank with warm water, you may require a correction there. But then again, you would want that for your ion chamber too. Usually best not to scan in warm water. It does have a very small spot size. That 1 millimeter resolution makes it nice for high accuracy of measuring your penumbra or measuring output in the center of those very small fields. And we also do make an MR compatible, well, the fiber itself is MR compatible. We sell it as an MR compatible kit where essentially it's a longer fiber that's provided so that the electronics can stay outside the 5 Gauss line. But there is nothing ferromagnetic within this fiber at all. Limitations of the W2, as I mentioned, the plastics degrade with age, so it does require an occasional recalibration or recharacterization as the fiber ages. And then the optical signal measurements are non-intuitive to many users. I've heard a number of people say there's a bit of a learning curve with it. As you get used to how this detector works and what sort of signals you can expect from it, and that sort of thing, excuse me, it does take a little while to get used to, but the people who have gone through that learning curve are usually very happy with it. The low signal to noise ratio, just because this is a low signal device, does mean that your scanning needs to be done at a slower rate. We usually recommend about a second measurement dwell time at each measurement point. That said, when you're scanning at that speed, you don't have to scan with a reference detector. You can just scan with the fiber itself, if you wish. Proof is in the pudding, of course, in terms of scanning. This is a plot from a publication from Paulina Galavis looking at radiochromic film compared with the W2 when the W2 was first released. And we got excellent agreement both in the shape of the penumbra, the measurement of the dose out of the field, and the overall scanning resolution. They were very happy with it anyway. So with that, that was what I was going to tell you about small field scanning. Hopefully you feel like you have some options now. There are some tools available to help you. If you have questions, please feel free to enter them here or follow up with us afterwards. Otherwise, thank you so much for your attention, and I look forward to talking with you in the future.